Well, hello, and welcome back, ladies and gentlemen. This is Chapter 2.7, and in Chapter 2.7, we're going to be graphing absolute value functions and working with their transformations. So, major goal of this video here is being able to graph an absolute value function in this form, y equals a times the absolute value of x minus h plus k. So let's learn about how we do that. So, first of all, we want to talk about parent functions. We talked a little bit about a parent function when we were doing linear. So there is a family of absolute value functions. The parent function of that is f of x equals the absolute value of x. So this is a plain absolute value graph that has had no transformations done to it. All absolute value graphs are V-shaped and symmetric about the y-axis. So for every point on xy on a graph, the point negative xy is also on the graph. So let's show an example of that real quick. Let's take this parent function, and I want to first of all, I want to put the right number the right thing in that spot. This is going to be x over here, and this is f of x over here. Remember, it could also be y. And I'm just going to plug in a bunch of numbers, okay? And notice that I'm just going from -3 to 3. I'm getting an idea of the behavior of this function, the absolute value of x. So let's plug in the numbers and find out here. I'm going to go from the bottom to the top. So when I plug in 3, this becomes the f of x equals the absolute value of 3, which is 3. So this is 3. And when I plug in 2, this is the absolute value of 2, which is 2. And when I plug in 1, this is the absolute value of 1, which is 1. For 0, this is the absolute value of 0, which is 0. Now, for -1, remember, this is the absolute value of -1, which is +1. It's going to do the same thing for -2, and it's going to do the same thing for -3. Remember, the absolute value of a negative number is a positive number. So when I plug in points, I get a much different looking graph than a straight line. If this were a straight line where f of x equals x, when I plugged in the negative numbers, I would continue to go down. But that thing is, every time I plug in a negative number, it's being changed positive because of the absolute value. So my points here, -3, 3, -2, 2, -1, 1, 0, 1, 1, 2, 2, 3, 3. Notice the shape of this graph. It's a straight line, but at some point, it gets kind of bent, right? So it was going straight, and then it bounces off the x-axis, and it comes back up here. So notice that this is that V-shaped, symmetric about the y-axis shape. If you were to draw an invisible line right here on the y-axis, you could fold this over that invisible line. So all absolute value graphs look like this, and they look like this because when you plug in a negative number, it bounces up, right? When you plug in something that makes the inside negative, it bounces back up. So all absolute value graphs have this V-shaped, symmetric about the y-axis shape. However, we can do some transformations to this graph. So this right over here is the parent function, meaning it is the function that has been unchanged, okay? This parent function is going to give birth to a family of functions based on a bunch of transformations that we can do to it. So we've got 3 different types of transformations. We've got translations, which shift up, down, left, and right, right? So I'm just moving it around, not changing the shape of it, just moving it up, down, left, right. I've got dilations, which are going to be shrinking and stretching it. And then I've got reflections, which are going to flip it over the x-axis. So a reflection is going to flip it upside down. The stretching or shrinking you might make a V that is really, really stretched out, right? Or you might have a V that is really thin, maybe even thinner than that, right? Super thin. So dilations, stretch, or shrink, and then translations just move it around, right? They just change it in direction. Well, in the function for an absolute value, we have ways to see the transformation. So the family of absolute value functions can be derived through the use of any combination of transformations and is defined as this formula. Okay? The translations, the shiftings up and down and left and right, they come from the h and the k. And as it turns out, the h value shifts left and right, and the k value shifts up and down. So these two values, the one adding or subtracting inside the absolute value and the one adding and subtracting on the outside, are causing left-right shifts. H is moving left-right, K is moving up-down. The dilations come from the A value. So the A value, will do the stretching and the shrinking. And in all honesty, it works like slope. You should think of the A value as your slope. It's changing how steep the line is. The reflections happen when we have a negative A value. Anytime your A value is negative, again, this one that's multiplying the front, if it's negative, we flip it over. Okay, so these are the fundamentals. We're going to do a bunch of examples. So go ahead and we're going to do those in the next video, though. So thank you for watching this one. And in your Canvas, you're just going to go to the next part of your lesson and check out the next video. All right, so we'll see you in just a minute.